Right now, in the middle of the Sahara Desert, there is a structure so large that it is visible from orbit. It is perfectly circular. It measures 50 kilometers across. Geologists have studied it for over 60 years. They have taken satellite images, drilled core samples, and run every geological test modern science has available. They still cannot agree on how it was formed. That is just one of the 8 landforms we visit today. We are not talking about places that simply look unusual. We are talking about formations where the most credentialed geologists, biologists, and atmospheric scientists in the world have taken samples, published competing papers, and still cannot reach a definitive conclusion. Before we are done, you will see the desert floor of Death Valley covered in rocks that physically move on their own, changing direction mid-path without any visible force. A lake in Western Australia so consistently and completely pink that photographs of it are routinely dismissed as digital composites, and a ring in the Sahara so vast that the International Space Station crew uses it as a navigation landmark above a continent full of cities. 8 landforms, 8 debates the scientific community has not resolved. Some have theories, some have competing theories that directly contradict each other. None have definitive answers. We begin in Death Valley. On the floor of a dry lake bed in Death Valley National Park, California, rocks move. Not metaphorically, not slowly in the geological sense, where movement is measured across thousands of years. The rocks physically relocate, leaving behind long trails in the dried mud. Trails that stretch for hundreds of feet, change direction mid-path, run parallel to each other, and in some cases make sharp turns of 45 degrees or more. Racetrack Playa sits at an elevation of 3,608 feet above sea level, in one of the most inhospitable environments in the Western Hemisphere. The lakebed is almost perfectly flat, with a surface variation of less than an inch across nearly 3 miles of dry terrain. The rocks that move range in weight from a few ounces to several hundred pounds. For over 100 years after the phenomenon was first documented by scientists in 1948, nobody had ever witnessed a rock actually move. The trails were real. The rocks were real. The mechanism was completely unknown. Multiple theories emerged over the decades. Dust devils, earthquake tremors, bacterial mats reducing friction beneath the rocks, sheets of wind-driven ice. Each theory failed to fully account for what the trails were showing. The sharp turns, the parallel lines, the differing distances covered by rocks sitting only feet apart. In 2014, a research team from the Scripps Institution of Oceanography installed GPS trackers inside rocks and directly documented the mechanism for the first time. After rare winter rainfall floods the Playa to a depth of a few inches, nighttime temperatures cause thin sheets of ice to form. When the sun rises, the ice breaks into panels. Wind then drives these panels across the flooded surface at speeds of 3 to 5 miles per hour. The panels push the rocks, and the rocks leave the trails. The mystery is not entirely resolved. The conditions required are so specific: precise water depth, correct ice thickness, adequate wind speed, that the mechanism was directly observed on only 2 occasions between 2011 and 2014. In most years, Racetrack Playa is completely still. The rocks have moved. There is no ice. There is no current explanation for those movements. In the Namib Desert along the coast of Namibia, the landscape for thousands of square miles is covered in circles, not random patches of bare ground. Circles, perfectly round, ranging from 7 to 49 feet in diameter, spaced with a regularity that suggests deliberate pattern rather than chance. Each bare patch surrounded by a ring of taller, denser grass at its outer edge. From the air, they look like something printed onto the land rather than grown from it. The circles number in the millions. They have existed for as long as oral history in the region extends back, and likely far longer. Scientists call them fairy circles. They have been studying them for decades. Two primary competing theories currently dominate the published literature, and as of the most recent peer-reviewed research, neither has been conclusively proven over the other. The first theory proposes that colonies of sand termites excavate the root systems of grasses within each circle, creating a bare patch that functions as a water reservoir, allowing the colony to survive the extreme aridity of the Namib. The second theory, developed by mathematical ecologists, proposes that the circles emerge through competitive self-organization, grasses naturally spacing themselves to avoid competing for the same limited water supply, with the bare circular patches simply representing the zones where no grass can win that competition. The mathematics of this model generates patterns nearly identical to those on the ground. In 2016, a joint study proposed that both mechanisms operate simultaneously. This partially satisfied neither camp. Field measurements show termite activity present in some circles, but absent in others. The mathematical model predicts the spacing accurately, but cannot explain why termites appear specifically where they do. In 2023, fairy circles were identified in arid regions of Western Australia under entirely different ecological conditions, raising a further question that neither theory fully answers. If two separate environments on opposite sides of the planet produce the same phenomenon independently, can any single organism explanation be correct? The circles remain. The consensus does not. In the northeastern corner of Wyoming, rising 1,267 feet above the surrounding plains, stands a geological formation that has no obvious reason to be there. Devil's Tower is a monolith of igneous rock, roughly cylindrical, with a flat summit covering approximately 1.5 acres. Its sides are covered from base to top in spherical columns, hexagonal, pentagonal, and four-sided prisms of phonolite porphyry that average 6 to 8 feet across and run the full height of the structure in near parallel lines. The surrounding landscape is rolling sedimentary terrain. The tower rises from it with no comparable formation within several hundred miles in any direction. Geologists agree on the general classification. Devil's Tower is igneous intrusive rock that formed underground. What they continue to debate is the specific mechanism. The dominant theory holds that it is the cooled core of an ancient volcanic neck, the solidified magma column that once fed a volcano whose outer structure has been entirely removed by erosion over millions of years. A competing theory suggests it formed as a laccolith, an intrusion of magma that pushed upward between sedimentary layers and never breached the surface. The vertical columns are explained by the contraction of cooling magma, a process called columnar jointing that is well characterized in geological literature. What is less understood is why the columns at Devil's Tower are so regular, so consistent in cross-sectional dimensions, and so nearly perfectly vertical across a height exceeding 1,200 feet. Columnar jointing at most other locations produces formations that are crooked, irregular, and variable. At Devil's Tower, the result approaches geometric precision at a scale that the standard cooling model does not fully account for. Devil's Tower holds sacred significance for more than 20 Native American tribes. The Lakota name for it is Matotipila, the Bear Lodge. The name reflects oral traditions that predate geological investigation by centuries. The science reflects a debate that has continued for 150 years without resolution. Every winter in Alberta, Canada, a reservoir called Abraham Lake freezes over. What forms beneath the surface ice is unlike anything else in the geological record. Viewed from above on a clear winter day, the transparent ice reveals thousands of white disks suspended at different depths beneath it, some within inches of the surface, some several feet down, stacked in vertical columns that rise from the lakebed toward the light. Each disk is a pocket of methane gas, frozen in place as the lake surface solidified around it. Abraham Lake is a man-made reservoir, constructed in 1972 by a hydroelectric dam on the North Saskatchewan River. The flooding of the surrounding terrain submerged what was previously forest and meadow, and as the organic material on the lake bed decomposes, it produces methane. This process is understood. The specific visual phenomenon is not. The bubbles do not appear uniformly across the lake floor. They cluster in defined locations, forming columns and groupings with a spatial regularity that implies gas is rising from specific structural points in the lake bed, rather than from random decomposition throughout. Scientists have mapped the cluster zones and identified areas of concentration. The subsurface structure, creating these points of preferential gas release, has not been fully characterized. The preservation of the bubble columns during freezing is also not fully explained. Abraham Lake freezes in a way that maintains the stratification of bubble sizes and depths, smaller bubbles near the surface, larger bubbles below, in a clear ice column that allows full visual access. The specific combination of water chemistry, temperature gradient, and reservoir flow dynamics that produces this unusually photogenic outcome has not been documented in comparable detail at any other methane-producing lake. The lake freezes. The bubbles appear in the same pattern each winter. The reason the pattern is what it is remains an open question in the literature. On Koekoe Beach, on the eastern coast of New Zealand's South Island, the shoreline is scattered with spherical boulders. Not approximately spherical, not rounded with a roughly ball-like appearance. Geometrically, measurably close to perfect spheres, ranging from 1.5 feet to nearly 10 feet in diameter, weighing up to 7 tons, sitting on the sand in configurations that give no immediate indication of any natural origin. The Moeraki Boulders formed inside seafloor sediment over approximately 4 million years through a process called concretion. Mineral, primarily calcite, precipitated around a central nucleus, such as a fragment of bone or shell, accumulating in layers as the surrounding sediment compacted. This process is well understood. Concretions form in sedimentary environments worldwide. What is not well understood is how concretion produced spheres this large, this heavy, and this geometrically regular with such consistency at a single location. At most concretion sites worldwide, the formations are irregular, flattened, elongated, asymmetrical in ways consistent with inconsistent mineral deposition and variable compaction pressure. The Moeraki boulders are round to a degree that the standard concretion model does not fully explain. When fractured, the boulders reveal septarian patterns, networks of yellow and brown calcite veins radiating from the center in structures resembling the chambers of a broken geode. These form when the concretion dries during diagenesis, cracks internally, and different minerals fill the resulting fissures. The process is documented. The product, a multi-ton sphere of geometric precision with a complex internal mineral architecture, is not replicated at this scale anywhere else in the known geological record. Maori tradition explains the boulders as the scattered remains of food baskets and calabashes washed ashore from the wreck of a mythological canoe called Araituru. Geology explains them as concretions and acknowledges that the mechanism behind their unusual precision remains incompletely characterized. On Middle Island, off the southern coast of Western Australia, there is a lake that is the color of bubblegum. Not pink-tinged, not pink under certain lighting conditions. Uniformly, consistently, permanently pink, a color so saturated and so unlike any natural body of water that images of Lake Hillier are frequently dismissed as digital composites by people seeing them for the first time. The lake was first documented in 1802 by British navigator Matthew Flinders, who recorded its rose-like color in his expedition journals. More than 200 years later, the cause of that color is still a matter of active scientific investigation. The leading hypothesis involves a combination of halophilic microorganisms, organisms that thrive in high salinity environments. Lake Hillier has a salinity level comparable to the Dead Sea. Several species of halophilic bacteria and archaea are known to produce pink and red pigments as metabolic byproducts. The pink alga Dunaliella salina, which produces beta-carotene, is also present in chemically similar pink lakes elsewhere in the region. What distinguishes Lake Hillier from those other lakes is that the pink color does not disappear when water is removed from the lake. Water taken from Lake Hillier in a container remains pink. At other pink lakes in Australia, the color is entirely dependent on the living organisms present and fades when separated from the lake environment. At Lake Hillier, the color is persistent. This implies that either the pigment concentration differs in kind rather than simply in degree, or that a chemical process independent of the living organisms is contributing to the color. A 2015 molecular biology study identified more than 36 species of microorganisms in Lake Hillier, many of them previously unknown to science. The study concluded that the interactions between these organisms are complex enough that no single explanation for the color has been confirmed. In Gansu province in northwestern China, a range of mountains appears to have been painted by hand. The Zhangye Danxia National Geological Park covers 510 square kilometers of layered sandstone formations in bands of red, orange, yellow, green, and blue that run horizontally across cliff faces in saturation that is visible from low-flying aircraft and unmistakable from the ground. Danxia landforms in their basic mechanism are understood. The colored layers represent different periods of sedimentary deposition over approximately 24 million years. Red layers indicate iron-rich depositional periods. Greens and blues reflect periods where other mineral compounds dominated. Tectonic uplift and subsequent erosion exposed the bands and sculpted the current formations. What remains incompletely explained is the intensity of the colors. Sandstone formations at other locations worldwide show color variation consistent with mineral content, but the saturation at Zhangye Danxia is measurably higher than models based on known mineral concentrations would predict. Laboratory analysis confirms elevated iron oxide levels in the red layers, but the specific conditions under which the iron oxidized, the precise atmospheric temperature, humidity, and chemistry of the ancient environment have not been reconstructed with confidence sufficient to explain the observed intensity. The green and blue layers present a more fundamental problem. The mineral compositions that produce these colors in sedimentary rock typically require reducing conditions, depositional environments low in available oxygen. These layers sit in direct stratigraphic contact with the iron-rich red layers, which require oxygen-rich conditions. The alternation between reducing and oxidizing environments occurring repeatedly within the same geological column implies a sequence of atmospheric changes that does not correspond cleanly to any current model of regional paleoclimate. Tourists visit in numbers exceeding 1 million per year. The chemistry of the colors remains a subject of active research. In the western Sahara Desert in Mauritania, a circular formation 50 kilometers, 31 miles, in diameter sits in one of the most remote and least visited regions of the African continent. It is composed of concentric rings of eroded rock, alternating between harder and softer geological layers, producing a target-like pattern that is clearly legible from orbit. The crew of the International Space Station uses it as a navigation landmark. They see it before they see most African cities. The Richat Structure, the Eye of the Sahara, called Richat in Arabic, was classified as a meteorite impact crater when first formally described by geologists in the mid-20th century. The concentric circular form, the scale, and the presence of high-pressure rock deformation all appeared consistent with an impact event of considerable magnitude. That classification was subsequently challenged and largely abandoned. The structure lacks several key indicators of impact. There is no shock metamorphism in the rock record of the type that meteorite impacts produce. No extraterrestrial material has been identified, and no impact melt sheet has been located beneath the formation. Scientists then proposed a revised origin, a symmetrical dome of rock that formed through volcanic uplift and was then eroded over tens of millions of years by wind and water, with the concentric rings representing successive layers of harder rock exposed as softer material was removed. This theory also has problems. The degree of symmetry in the Richat structure is unusual for an erosional dome. Natural erosion typically produces irregular patterns because rock hardness varies. Near-perfect circularity over a diameter of 31 miles requires either an unusually uniform initial dome or a mechanism that has not yet been identified. A third class of hypothesis, less accepted in mainstream geology but present in peer-reviewed literature, involves a hydrothermal origin. A dome formed by the upwelling of hot, mineral-rich water through underlying rock during a period when the Sahara contained water rather than sand. Three major theories, 60 years of investigation by some of the most well-funded geological institutions in the world. A structure 31 miles across that formed in one of the most geologically studied regions of the African continent. The question of its origin remains open. From the self-propelled rocks of Death Valley and the unexplained circles of the Namib, to the frozen methane patterns of an Alberta reservoir and the spherical impossibilities on a New Zealand beach. From Wyoming's geometric monolith and a permanently pink lake in Western Australia, to Rainbow Mountains in China and a 50-kilometer ring in the Sahara that three separate theories cannot fully account for. 8 landforms. The explanations that exist for each are the best available, built on real fieldwork, real samples, and real analysis by scientists who have dedicated careers to understanding them. They are also incomplete. This is what geology actually looks like when it is being practiced rather than reported on. Competing models, insufficient observational data, phenomena that are too large, too ancient, or too rare to observe in full. The Earth produces formations on timescales that make direct observation impossible and leaves evidence that points in more than one direction. What you have seen today are not the exceptions to how science works. They are the most accurate version of how it works, with precision where precision is achievable, and with acknowledged uncertainty where it is not. Which of these 8 landforms do you find most difficult to accept as the product of natural processes alone? Let us know in the comments below.